Hello everybody and welcome to this month's Pavinar. Today we'll be talking about Portland cement concrete overlays. The logistics of the series is that if you have a question, please raise your electronic hand by clicking on the hand icon that you can find above the list of participants on the left side of your screen. And when I see a hand raised, I will pause for a convenient break and you can type the question into the chat box, and then I will answer the question. And you can find the chat box on the lower left-hand side of the screen. As always, professional development hours will be emailed to you after the presentation. And I'm excited to say that we do have a new website. It's www.pavinars.com. I'm putting that into the chat box now. And that will be the website that we will use moving forward. As mentioned, today we will talk about Portland cement concrete overlays. We'll start out with a background. Why do we use concrete overlays, and what are the two primary types of overlay systems? We'll also talk a little bit about evaluating existing pavements to determine if overlays are an appropriate solution to the problems that you may be having on the roadway. The two overlay systems that we'll cover are bonded and unbonded overlay systems. There's different configurations of these, but at the end of the day, you can split Portland cement concrete overlays, or PCC overlays, into two pretty distinct groups, bonded and unbonded. We'll cover some designs, information about overlays, including the inputs you want to use, some design selection guidelines, and also materials. And we'll finish up with a little bit of construction, including what you do pre-overlay, the preparation work you do on the roads, the actual concrete placement, and then of course with any concrete roadway you need to worry about the joint sign as well. And a lot of this information I obtained from the Guide to Concrete Overlays, which was put out by the National Concrete Pavement Technology Center. And the link on your screen does not work within Collaborate, but the link in the chat box does work. So as I mentioned, most of the information I got from this presentation is from that document. Lots of good information over there. I'm not going to be able to cover it all in this presentation, but it's definitely a good supplement to what we'll talk about today. So the question we can ask ourselves is why Portland cement concrete, or PCC, overlays? And you can see here an example of a pavement condition curve. So on the y-axis here we have a pavement condition rating, or PCR, and this is commonly used in the state of Washington. It's a type of pavement serviceability index type thing. On the x-axis we have the years of the road, and that is in the age of the road in years. And you can see as the pavement condition rating deteriorates, this tends to happen over time. So if a roadway is set to last here in this example for 20 years, if you do no maintenance or rehabilitation, you would accept it to dip under the 40 rating. Now what I really like about this slide, however, is the dollar amount that is assigned to each pavement condition rating. So in this graphic that Taylor provided in 2012, they split the pavement condition rating into 4 different sections, from 60 to 100, from 50 to 60, from 40 to 50, and 0 to 40. And you can see here where if you spend $1 in maintenance between that 60 to 100 rating, any $1 spent there is equivalent to anywhere between $4.80 and $7 in the 50 to 60 range. So once the pavement starts deteriorating more significantly, your costs go up almost 5 to 7 times. If the pavement continues to deteriorate down into that 40 to 50 range, it costs $20 to fix what would have cost $1 originally. And then finally, when you slip under 40, which is down in the very poor section, it costs $48 for every $1 that you would have originally spent. And this is a discussion that is often talked about in the pavement industry, is how do we balance the fact that obviously there's limited amount of monies available for maintaining our road network and building our road network, And is it worth bringing those very poor roads, which are 48 times more expensive to bring up into a good condition, is it worth maintaining those at the expense of letting other roads further deteriorate? And I have a feeling if there was an easy answer to that question, people wouldn't be talking about it. So, but this is a very nice demonstration, though, about how the further we let roads deteriorate, the more that it costs to bring them up into serviceable conditions. What are some benefits of PCC overlay? One of the key points to PCC overlays is you need a stable and a uniform base. Just like really any pavement strategy, what lies beneath is just as critical as what is on top. So if you have a stable and uniform base, PCC overlay should be able to extend the life of the pavement up to 30 years. One of the benefits is if you have a pavement that has pretty significant surface distresses, you don't need to remove any of the existing pavement. The overlay can simply be placed on top. And along those lines, although you want to make sure you are structurally sound, the pre-overlay repairs are minimal. So if you're structurally sound and you have a highly cracked road or even a rutted road, the industry believes that you need to do minimal repairs on those in order to bring it up to the level where the overlay can be placed. A benefit of it is also no specialized equipment is necessary. So a typical paving train for like a screed and the concrete trucks, it's the same equipment that you'd use for a traditional Portland cement concrete job. You can see over there on the right the picture. They're placing new concrete along a little windrow there, and that concrete truck in the center of the picture, not the one delivering the concrete, but the one in the other lane, that's actually traveling on a thin overlay. And if you look kind of closely right under where that concrete is being delivered, the fresh concrete, you can see that concrete overlay. It's about 3-4 inches thick. So these are often a little thinner than your traditional concrete pavements. This is another take on the slide image that we saw on slide 5 with the pavement condition rating. As time goes on, your pavement condition deteriorates. It starts at excellent and can go all the way down to fail. And here what the National Concrete Pavement Technology Center came up with is just a little schematic to start talking about what sort of things need to be done. So as you're going down that curve, you go from preventative maintenance to minor rehabilitation to major rehabilitation all the way down to a full reconstruction. So that's kind of how the pavement deteriorates and what sort of things you're looking at doing once a pavement reaches that stage. And you can see there on the far right, they have our two types of overlay systems. You have your bonded system and your unbonded system. And you can see where the pavement condition needs to be in order to apply some of these treatments. So if you have a good road, if the pavement's in good condition, you can consider using a bonded overlay on concrete or a bonded overlay on asphalt or composite. However, as you start going down that pavement condition curve, as the condition of the pavement goes to fair and poor, they start going into the unbonded materials. So really, in order to get the full benefit of this bond, and we'll talk about this throughout the whole presentation, bonded versus unbonded, but in order to get the full benefit of this bonded system, you really do need to have the existing pavement condition high, and then you're able to use that bonded technology. Here are just some schematics of both our bonded overlay systems and unbonded overlay systems. So the bonded overlay systems are on the left and the unbonded overlay systems are on the right. And as you go down the screen, you can see we have the bonded concrete on concrete, bonded concrete on asphalt, and then bonded concrete on composite pavements. And the picture here of the composite pavement is Portland cement concrete road with an asphalt overlay, and then the bonded overlay system on top of that. So you kind of have an ice cream sandwich of sorts with two cookies and then the asphalt in between. And then on the right-hand side, the unbonded systems, you have the concrete on top of concrete, you have concrete on asphalt, and then the concrete on the composite, which again is the asphalt over the concrete. And you can see here the the Technology Center spent some time trying to make sure that all of this terminology is on the same page. So you probably have heard of ultra-thin white topping, conventional white topping, these type of things. Ultra-thin white topping is specifically bonded concrete overlays of asphalt pavement, whereas the conventional white topping is unbonded concrete overlays of asphalt pavement. So you have kind of these terms that have been floating around for a couple of years, and the Technology Center has tried to establish these new bonded and unbonded terms as the way moving forward on how to refer to the systems. So when you're thinking about what, just kind of a general overlay, these bonded overlays, they add some structural capacity. You can eliminate any sort of surface distresses, again, when the existing pavement is in good structural condition. So if you feel like you have a pavement in good structural condition, you can simply place an overlay on top of that, and you don't need to worry about taking care of those surface distresses with any sort of rigor. It is essential to have bonding, just like asphalt concrete overlays. If you do not hold and maintain that bond, you will not be able to get the full benefit of that added structural capacity. And we'll see that in the upcoming slides about how these loads are actually transferred down through the pavement structure. As far as unbonded overlays go, these are meant to go on top of pavements that have some structural deterioration. So you're looking to add a little bit of structure to the pavement. And basically what you're doing is you're building a new pavement on an existing stable platform. So the platform is stable. Your existing pavement structure is stable. It's not necessarily structurally sound, but it is stable. And that is the new platform for the road that you put on top, the new PCC overlay that you put on top. And here's the idea of the bonded versus unbonded layers. You can see with the bonded layers, you only have one neutral axis. That's what the NA is, and that's where you go from compression to tension. So on a bonded concrete pavement, on a bonded PCC overlay, you have your neutral axis kind of toward the lower part of your overlay. Above that neutral axis, closer to the road, you have compression in your pavement structure, and below that neutral axis you have tension, and you can see that the tension transfers through that bond into the lower layers, and it keeps on going in tension. Now, because they're different thicknesses, you have a different slope, but the tension is transferred because it's a bonded surface. And you can compare that to the figure on the right, which is an unbonded surface, and the neutral axis is directly in the center of each one of those layers, and both layers have both tension and compression with them. So the mechanism of how the pavement reacts to the loads on top of these surfaces is quite different, and this will influence a whole variety of factors, including materials, thickness design, and those type of things between the bonded and the unbonded layers. And when you're thinking about what do we need to ask ourselves, what questions do we have when we're evaluating our existing pavement? Well, understanding what is in place is absolutely critical. So you want to know the presence, the type, and the extent of the distresses that you have. These type of qualifications can determine whether it's a bonded or an unbonded layer. You want to know what the structural condition is and also what the load carrying capacity is. So this is where like a falling weight deflectometer, an FWD, would come in handy to know what kind of pavement layer is already in place and what are you getting out of that, and also knowing what do you need in addition in order to have your road serviceable. It's important to know some of the functional characteristics, and functional characteristics include items such as roughness, friction, and the noise. This will help you understand what you're going to be putting on top and how that's going to interact with what's in place. And then finally, you want to know the behavior of the in-place materials. What's actually happening in that pavement at the time. Is the subgrade in good condition? Is the subbase in good condition? Do you have pumping? Is water coming up to your roadway? All these type of things. These are just good things to know about roadways when you're doing any sort of evaluation on them. And they encourage you to look at historical data, to perform a visual examination, if possible, to get some cores of the pavement. That'll tell you a lot about the characteristics of those layers. And then you can also perhaps even do some laboratory testing, and that'll allow you to get a lot of information about the performance of the road. And also, as we'll see in the design, there are potentials to use MEPDG, the Mechanistic Empirical Design Guide, which if you input material characteristics, it can really aid in the design of your roadway. So that's just a real brief background of PCC overlays, kind of the who, what, when, where, and why. And now we're going to go into the actual overlay system. So we're going to get into a lot more details about both bonded and the unbonded overlay system. If you have any questions, though, I encourage you to click on your electronic hand to raise your hand and then type the question into the chat box. Well, there don't appear to be any questions at this time, so we'll move on to the overlay systems. As I mentioned, there are two types of systems overall, your bonded and unbonded, and each one of these can be applied to existing PCC pavements, existing asphalt pavements, and then also existing composite pavements. So what we'll do is we'll just kind of go through these 6 different systems. We've got some nice graphics to kind of show you visually what is going on with each one of these systems. So the first one we'll cover is bonded overlays of PCC pavements. And what you have here is you have some sort of existing PCC pavement. So in the image to the right, the existing PCC pavements are these first 2 sections where you have your existing concrete pavement with surface distresses. Then going back a little further, you have your prepared surface. So these are the 2 existing pavements. You want to make sure they're structurally sound, but you can have surface defects. So you'll notice the spalling, these random cracking, the deteriorated partial depth patch, scaling, and transverse cracking. These are all surface distresses. So you don't see any sort of intensive full depth problems that would lead you to believe that you have any structural issues. Taking this section here and going back to the prepared surface, you can see they chose to perform a full depth patch to take care of the spalling, the cracking, and the partial depth patch. And then they had to clean up that transverse cracking and scaling. And then they were able to lay the new concrete surface on top of the existing concrete surface. The next surface you have is these bonded overlays of asphalt pavements. And again, these asphalt pavements are structurally sound, but you have extensive surface defects. So taking a look at the very first panel here, you have your existing asphalt pavement. Many surface distresses. You have rutting in the surface layer. You can see that rutting stops in the asphalt layer. It does not go down to the subgrade or subbase. You can have some potholes and bleedings, localized fatigue cracks or alligator cracking, some shoving, slippage, and then some normal longitudinal and transverse thermal cracking. So again, all of these stresses are happening in the surface of the pavement, and there's nothing structurally deficient about your pavement. How did they choose to take care of some of these issues? Going to the next panel back, the milled and cleaned surface, you have some full depth repair patches, and then you can see that the patches were applied to the potholes and some of the bleeding, some fatigue cracking. But then moving over to your shoving and slippage and the longitudinal and transverse cracking, they chose not to do any sort of maintenance on the longitudinal and transverse cracks. If the nominal crack width opening is less than the maximum overlay aggregate size, you do not need to fill those cracks. And the point of this is when you're putting that concrete overlay on, the theory is if the big aggregates can't go down into that crack, some paste will go down into there, but then you'll be able to bridge those cracks. And if the pavement is structurally sound and you can bridge those cracks, then the overlay will be able to be successfully applied. You can see here on these asphalt pavements, the overlay is approximately 2 to 5 inches thick, and you have those square panels as your overlay geometry. And then you can see here the composite pavement. This is very similar to the asphalt pavement we saw on the previous slide, but instead of just having an asphalt layer, you have a concrete layer with an asphalt layer on top. And you can see the same distresses are shown here. And then they do the same milling and cleaning of the surface, and then again they place the panels on top. But this is a very common pavement configuration in the United States because we have a lot of existing Portland cement concrete roads that have asphalt overlays on top of them. And a very traditional way to take care of these type of distresses is to do a mill and fill or a mill and replace, but another option is to do a bonded Portland cement concrete overlay. So those are the three types of bonded overlay systems on existing Portland cement concrete, on asphalt concrete, and then on composite concrete or composite pavements. Now we're going to take a little look at the unbonded layers. So here you can see a pretty significant amount of structural damage. So the PCC pavement is not structurally sound, and it can still have extensive surface defects. So you can see the partial depth patches, some cracking, both transverse and longitudinal, and some scaling. But then in that panel in kind of the left corner of the screen, you can see some ASR, which is alkali silica reaction. You have some pumping. Pumping of concrete pavements is definitely a signal that you have some structural issues. There's some decracking. That's another signal. You might have some material being lost underneath those corners. You can have badly shattered slabs and also spalling. That's the existing pavement condition, and you have to do some maintenance on this. They have a fold-up repair and cleaning and those type of things. And because this is an unbounded overlay, you can see in the very back we have an asphalt separation layer. And what that asphalt separation layer does is it provides a buffer between that existing PCC pavement and the unbonded overlay on top. So you have your two different pavement structures with your two different Portland cement concrete pavement structures with a relatively thin asphalt separation layer. And those asphalt separation layers are approximately 1 inch thick. Another thing I'd like you to note on the unbonded overlays is they added some drainage on the very right-hand side. And drainage of pavements is critical, making sure that water, especially if you have pumping, is taken out of your pavement system, directed to the sides, and then drained through pipes on the side of the pavement. So lots of things going on here, but at the end of the day, we're interested in knowing that the existing pavement is not sound, and that's the biggest difference between the bonded and the unbonded pavement layers. When we're looking at asphalt concrete, again, not structurally sound. And what does that mean? Well, that means that some of that rutting can actually be going down into the surface layer or into the subbase or subgrade. You can see that there's some waving going on of the roadway, and that indicates that the roadway is not necessarily on a stable foundation, or the loads being applied to the roadway are going above and beyond what the design was for those roads. But very similar types of distresses, your potholes, your rutting, fatigue cracks, block cracking, and those type of things. You can see some of the things that you may need to do. You may need to do some milling in order to kind of level the road out. And that's if you have a high level of surface distortions. You don't want to pave over a road that's very wavy, so you might need to do some milling, and we'll see some pictures of that later on as well. And then finally, in the very back portion, you can see the new unbonded overlay. It's a little bit thicker than the 2 to 5 inches that we were looking at before, but that's placed on top of the asphalt surface, and then you have those drains to the right. Then the final slide, just like in the bonded case, the unbonded overlays of composite pavements. It's very similar, the composite pavements, to the asphalt pavements. You have these extensive distresses in the pavement system. You need to either mill to get rid of the distortions. You may do some full depth repairs, but then you can place the unbonded overlay on top of that. So those are just kind of an overview of the 6 different systems they have, and you can kind of see the very broad scope that's available depending on what sort of condition your pavement is in, depending on what the structural capacity of it is. That just kind of gives you an idea of the systems. But again, if you have any questions now, please raise your electronic hand. And we've got one question. If you could type the question into the chat box, I'd be happy to answer. Looks like we have a couple questions, so as the questions are coming in, I'll answer them. So the question here is that there are issues with ASR, which is alkali silica reaction on the I-530 bypass, and what ASR areas have to be corrected before an unbound overlay is placed. And that is an extremely detailed question. And David, what I'm going to do is I'm actually going to get back to you on that, because it's my impression that on some of the more extensive distresses, they recommend a full depth repair. And ASR in particular, I'm not sure about. So what I'll do is I'm sure that there's been some research articles written on that, and I will get back to you on whether or not you need to do a full depth repair on ASR, or if that's something that can just be covered. The second question is from Tim Klein, and he asked, with a bonded overlay over asphalt, how important is the underlying condition of the bituminous layer? And if we're looking at a bonded surface, the underlying condition structurally is very important. Now, in theory, you are able to do some relatively minor repairs to get rid of the worst of the rutting or the cracking. But in theory, if you have a structurally sound layer, you should be able to place a bonded concrete overlay over that. It will bond together, and then you'll kind of get the benefit of having that thicker pavement structure, and that will allow you to have a higher load carrying capacity. So I think with the bonded overlay condition, the underlying, or bonding overlay, the underlying condition is more important, because you are counting on that to handle the structural capacity of the road, whereas with an unbounded layer, you are essentially having 2 different pavement layers and kind of almost 2 separate pavement structures. So I would say with the bonded overlay, it's the existing pavement condition is more important. All right, well, thank you for the questions. And so those are the 6 different types of systems. And now we're going to go on to an overview of the design of these systems. So we're thinking about what sort of inputs do we need to provide when we design the overlay systems. First, you need to characterize the existing pavement, and that includes doing the surface analysis and then also figuring out the structural condition of it. You want to do a traffic characterization, and depending on which pavement structure analysis you're using, that will be different. For AASHTO 1993, they just are concerned with the number of trucks or the number of easels, whereas with MUPDG, it's a more advanced system where they actually look at the distribution of traffic. So they look at how the distribution of the different types of trucks, and they can use that full distribution. They don't convert everything to a single type of vehicle as they do with easels in the AASHTO 93. For material properties, one of the most important is the degree of support beneath the structural layers. So whether you're looking at existing concrete pavements or existing asphalt pavements or existing composite pavements, what's underneath those pavements is also very, very important. And with soil materials, we consider that the modulus of subgrade reaction. But you'll see on upcoming slides where that degree of support is quantified changes based on the type of system you're using. Some other material properties of the overlay itself that are important are the strength of the modulus elasticity and the CTE of the concrete. And CTE stands for coefficient of thermal expansion. And this is very important because concrete is a mixture of aggregates and cement. And there can be some other things in there, but at the end of the day, the aggregates and the cement are the most important. And the CTE, the coefficient of thermal expansion, is how much does that pavement expand and contract as the temperature goes up and down. And you want to make sure that the CTE of the paste, which is the hydrated cement, is similar to the CTE of the aggregate that you're using. Because if your paste is expanding and contracting at a significantly different amount than the aggregates, then you could actually have debonding of the paste from the aggregates. And then essentially you have a very glorified, expensive gravel road because you no longer have that bonding, your concrete starts deteriorating, and you just have paste chunks and aggregates. So you want to try and match up the coefficient of thermal expansions. As in any pavement design, climate factors are critical. You want to know what kind of moistures you're dealing with. This is moisture coming out of the sky and also moisture coming out of the ground. And then what kind of temperatures you have too. Then finally, what kind of constraints are you looking at? Do you need to use a curb and gutter? If you're using curb and gutters, then the profile of your road becomes very important. Are you concerned about overhead clearance? If you're putting this on a road that has a lot of bridges going over it, you may need to do some considerations with how thick this overlay is in order to maintain proper overhead clearances. A very popular use of these concrete overlays is adding lanes on the side. However, that will start changing geometries, that'll start changing slopes of your road and final grades of your surface. So these are other types of constraints that come into play. And when you're thinking about how we actually going to design this pavement structure, the Technology Center, the National Concrete Pavement Technology Center, recommends one of three methods of designing your new roadway. You can use the AASHTO 1993 design guide, and for the rest of the presentation, I will simply call that the AASHTO method. An important note here is that the failure mode that you look at during the asphalt or the AASHTO design guide is your serviceability. So what is your serviceability rating, and that's what drives your failure. Another method that can be used is the American Concrete Pavement Association 2008. They have a program available. I'll call that ACPA. It stands for American Concrete Pavement Association. And they look at three different types of failure modes. They look at corner cracks, they look at plane failures, and they also look at asphalt fatigues. They look at the pavement layers below the concrete overlay. And if it's a concrete overlay over an asphalt material, that fatigue can start coming into play. And then the third one that we'll look at is the Mechanistic Empirical Design Guide, MEPDG. It's actually currently called Darwin ME. I kind of throw those in the same bucket though. That would make pavement designers cringe, but the MEPDG is the current method that's being used. And that failure mold is fatigue driven. And you can see this nice picture here on the right. You have an existing concrete pavement with a concrete overlay. And this is from FHWA, and you can see here that little slope on the side of the pavement is the safety edge. And that's to ensure that as cars kind of go to the left and the right, if they happen to run off the pavement, it's not just a 6-inch drop there, it's more of a slope where cars can safely go on and off the pavement without causing any sort of severe problems. It's obviously not encouraged, but it has helped with significant accidents. Now, something to be something that should be considered with any sort of concrete mix design is fibers. So fibers have started to be used in pavement concrete applications. You can have either steel or fiberglass fibers. I think I talk about those a little later on, and they've been covered in previous Pavinars, but only the ACPA street pave method, which is the ACPA 2008 method, includes fiber models. So if you guys are looking to use fibers, I encourage you to use the ACPA 2008 method. And we've got a message here from Tim Klein saying that MnDOT, Minnesota Department of Transportation, teamed up with a couple other universities, or excuse me, a couple other agencies in a pooled fund projects where the University of Pittsburgh developed a thin white topping design procedure called BCOAME. And thank you, Tim. That's the first time I've heard of that. So maybe during the next question I will question and answer period, I'll see if I can Google that and find a link to supply with the group. So when we're thinking about our design, two things pop out pretty quickly is joint spacing, whether or not a design method incorporates joint spacing or not into the design, and then also where do you take your K value, that modulus of subgrade reaction, where is it actually taken? We're used to seeing that taken on the top of the subbase, but depending on what system you're using, that changes. So let's just work through this table here. If we're looking at an existing PCC pavement, we can either use the AASHTO or the MEPDG design. And when you're thinking about joint spacing, what sort of methods will provide you with joint spacing guidance? Well, the AASHTO 93 method does not provide you with guidance, and the MEPDG assumes that your new joints match your existing structure. So the new joints will be on the existing pavement structure, or the same as the existing pavement structure. And the K value location is the same. It's the top of the subbase for PCC, both design methods. For asphalt, you have your three different methods. For the joint spacing, AASHTO does not have any recommendation, but ACP and MEPDG does give you information about what they recommend as a joint spacing. When you're thinking about the K value location, both AASHTO and MEPDG assume it's at the top of the asphalt layer. So when I think of K value, the first thing that pops into my head is the top of the subgrade. When we're thinking about these PCC overlays, that K value actually can be transferred up to the top of an asphalt layer. Or even with the ACPA layer, it's on the top of any non-stabilized unbonded base or the subgrade layers. So you have a little bit of a differentiation between AASHTO, MEPDG, and ACPA there. Between either the top of the subgrade or the unbonded base or on top of the asphalt. And you can see the same with the composite, AASHTO and MEPDG. The K value is at the top of the asphalt, where the ACPA is on the top of the non-stabilized unbonded base or subgrade layers. So trying to just understand what sort of joint spacing is recommended with each one of these systems and each one of these design methods, and then also where the K value is. And this is just for bonded overlays. And for unbonded overlays, it becomes a little simpler. You're only looking at the AASHTO and the MEPDG. And you can see here for unbonded overlays, AASHTO doesn't provide any sort of joint spacing for all three types, but MEPDG does. And then the K value location is the top of the separation layer. So when we were talking about unbonded PCC overlays, that's where you had existing PCC pavements. And you put that thin, 1-inch thick asphalt concrete separation layer, and then your second layer of new Portland cement concrete. You take the K value at the top of that separation layer, whereas with the asphalt and the pavement, or excuse me, the asphalt and the composite types, the K value is simply at the top of the asphalt layer. And I extracted this information on joint spacing and K value from a very large table from the Technology Center document. And that table also has a lot of information on deficiencies, shortcomings, or other items of note in each of the design consideration. So if these are details that are interesting to you, I encourage you to take a look at that link and move on. Now, before I go on here, we're kind of going away from the structural design and we're getting more into the material side. I'd like to point out that Tim has provided a link to the BCOAME So if you look down in the lower left-hand chat box, you can see a link to the Swanson School of Engineering where they talk about the design guide. They have a nice little practitioner's information, teaching tools, technical documentation, also sponsoring agencies, and also some user feedback. So it looks like a real nice resource there. And I apologize for not catching that when I did this preparation, but thank you for bringing it to our attention. So transitioning now into the materials. Just like regular Portland cement concrete that you use for conventional paving or structural application, you have some cementitious materials in here. And the Technology Center kind of divided these material decision trees into two different parts. If you wanted a conventional versus an expedited mixture. And when they say expedited mixtures, a lot of pavement design considerations are driven by how quickly can you return traffic to your pavement system. Obviously, the longer a road stays closed, the higher the user delays are, the higher the user costs. So expedited mixtures try and get those cars back on the pavement surface a little more quickly. And in order to get those expedited mixtures, you want rapid strength, and you can get that through high cementitious content, low water cement ratio, a smaller top size aggregate, or also you can consider using some admixtures. When you're thinking about the cementitious materials in general, and cementitious materials include both Portland cement, but they can also include fly ash, ground, granulated blast, furnace slag, and then there's several other much more rarely used cementitious materials. But Portland cement type 1 and type 2 are very commonly used. If you're looking for an expedited mixture, you can use type 3. But then fly ash and GGBS are two byproducts of industry. Fly ash is a byproduct of the coal industry, and GGBS is a byproduct of refineries. Those can also be used for cementitious materials. And on the right here is just a nice little picture I took on I-30 in Arkansas. You know, it's the first time I'd ever seen dowel bars on top of an asphalt pavement. They were putting some concrete overlays down, and they'd been lining the dowel bars up. But it's kind of a strange sight. You're not used to seeing that over an asphalt pavement. At least I'm not. When you're thinking about the aggregates as a material and your water to cementitious ratio, they recommend that the largest practical size of aggregate be used because the larger aggregate that you use, the lower amount of paste requirements you have, and the lower amount of paste requirements you have, the lower amount of cement. And cement is the most expensive component of concrete pavement, so you can reduce your costs. Also, by using the largest practical size, you can reduce your shrinkage, and you can improve mechanical interlock. So once that pavement does crack, and concrete pavements are designed to crack, where those joints are sawed in, you get aggregate interlock. And one of the last slides we'll show is a nice picture of a joint saw with the crack below that, and that aggregate interlock is critical. Important thing to notice also is that if you have uniform aggregate size, that can reduce shrinkage. And then finally, for aggregates, something that I talked about a little bit beforehand, the CTE, or the coefficient of thermal expansion, is important because the aggregates compose the majority of the PCC mass. So you want that aggregate to try and match the cement as close as possible, and the cement paste, and that will allow you to expand and contract at similar rates, and the durability of your road will increase. For the water to cementitious material ratio, 0.45 is common, but you can lower that if you want to reduce drying shrinkage, and you can also lower that if you want to expedite the curing and return to traffic. The final material we're going to look at is any sort of admixtures or fibers that you want to use. Two very common admixtures to use in pavement applications are air entrainments and water reducers. The air entrainers, they protect the concrete from freeze-thaw, so they essentially create thousands and thousands of little teeny bubbles that allows water to expand and contract and not deteriorate the pavement, but expand and contract into those small bubbles. It also prevents the pavement from deteriorating under de-icer scaling. So if you're in northern climates where you use a lot of de-icing agents, you can reduce the amount of scaling that could be associated with that using air entrainments. And the side benefit during construction is that you're able to increase your workability. The second admixture, water reducers, they allow you to lower your water to cementitious ratio while maintaining your slump, and you can also increase your strength and reduce your permeability. Along with admixtures, another type of admixtures, they have their own category though, is fibers. And if you add fibers to your mixes, it can increase your durability, it can improve your flexural ductility and toughness, your fatigue capacity, any sort of abrasion type, deterioration, also impact resistant. And there are two different types of fibers that are commonly used. You have synthetic and steel fibers. Synthetic can be broken down into polypropylene or polyester. This is basically like small plastic fibers, and you want to make sure those are dispersed nice and good through the mix. Sometimes they clump. If you put these bags in, you'll have a big ball of fibers. You want to try and make sure that it gets mixed as well as possible. And then also some people have played with blending synthetic and steel fibers. So there's a lot of interesting literature out there. There's a lot of interesting research about incorporating synthetic fibers. I know that Amanda Bordelin, she did her PhD at the University of Illinois. Now she's over at the University of Utah. She did a lot of work with fibers and pavement applications, so I definitely think there's some benefits to that. So that's just some ideas on the design of overlays, including some of the inputs you need, what sort of design selection you're going to use, and the materials. And what we're going to do is we're going to finish up with construction, where we'll talk a bit about what we need to do during the pre-overlay timing, actually when the concrete's being placed, and then some joint sawing as well. But if there are any questions, I'd be happy to take them. Well, there don't seem to be any questions at this point, so we'll move on to the construction. The first step of construction is making sure that you have good grade control. At the end of the day, the thickness of your concrete layer and the final grade of your pavement is very important to match with what the existing pavement has in place. So they recommend that you measure off your existing pavement or the top of the milled surface to set the string line. So make sure you know what's in place, and then you base your string line directly off of what is in place. And they recommend that you survey every 100 to 500 foot cross sections when you're shouldering, working with your fore slopes or back slopes, if any of those need adjusting. And this just ensures as you go down your job site, you're maintaining the proper thickness of the layer that you'll put on top of there. This becomes even more important as you're trying to use thinner concrete layers, because small changes in thinner concrete layers can have very significant repercussions of your pavement performance. You want to make sure that you survey kind of traditional problem areas, which could be bridge tie-ins, any sort of bridge clearance, and also extreme super elevations. So areas where you kind of have unique situations, you want to make sure you survey those areas. And then finally, you also want to, or you have the ability to use concrete to make up any 3-inch or greater variances in grade. And the point of this is that they're discouraging you from changing the thickness of that 1-inch separation layer, and in turn transferring that thickness variation to the concrete layers. The next thing you want to do is any sort of pre-overlay repairs. This ensures your uniform support. So if you do have deterior areas, you would want to remove those deterior areas and replace. And don't worry, David, I have a note here to get back to you on the ASR in particular. You can see here a picture of, looks like there is either a little bit of corner cracking or some sort of deterioration of the corners there. They just simply cut that out and replaced it. And if you have any sort of distresses that were not solved with milling, you can simply thicken the overlay. It's very important to repair the subbase when there's evidence of active movement. So we talked a little bit about pumping in a previous slide. If you do see pumping, material coming up into the pavement layer, then you want to make sure to address that issue before moving on, because if you're building on a weak support, it really doesn't matter what you're going to put on top of that, you're going to have problems down the road. And then also something important to be pointed out is that if you have some faulting along your projects, if it's what they call minimum faulting, they didn't quantify that, but if it's minimum faulting, you can simply just bridge it with an overlay, so you don't need to go in and diamond grind that off. The next step is your surface preparation. So you can either use shot, sandblasting, or milling to ensure your surface roughness for bonding. So that bonded layer, if you're using a bonded system, you want to make sure it's a rough layer so there's a lot of contact area. If it's a very smooth, glassy layer, you may not get the bond that you're looking for. If you do have any significant deterioration or high spots, you can mill that area. And you can see that occurred on this. This is another picture from I-30 in Arkansas. They did some spot milling to get rid of those significant distortions so you have a nice level surface to pave on. After you've done any sort of sandblasting or surface roughness or milling to make your foundation for the new pavement, you do want to make sure that you sweep that surface. And if necessary, you can also air blast that, and that'll make sure to get rid of any sort of particles so you can get that good bonding. Now we're working with concrete here, and concrete needs water to hydrate. Something that can happen is if you put a concrete material on a bone-dry surface, water will wick down into that surface, and you'll lose water from your concrete paste, and you'll have problems with your hydration. So you want to maintain the saturated surface dry condition. And what that means is you don't want pool water, you don't want water standing on your roadway, but you want water to be immediately under that surface. So the surface doesn't have standing water, but immediately under that surface you do have water, and that will prevent water from wicking down into the existing pavement. And obviously if you're going to use your unbonded PCC on an asphalt, or if you're using your unbonded PCC on a PCC surface, you want to place that asphalt separation down beforehand. Now, when you're actually constructing the concrete pavement, they do recommend that you use surface watering. This reduces the temperature of the pavement and it reduces shrinkage cracking. Again, you don't want to have a pond out there, but you do want to have that surface moist. As in any paving operation, asphalt or concrete, in concrete it's a slip form, in asphalt it's an asphalt paver. The number of trucks dictate your slip form speed. The worst thing you can do is you can stop your slip form, because then you'll have to cut a new joint and restart the whole process. So if you don't have a whole lot of trucks, slow down your paving speed to make sure that that slip form is always moving forward. When you're placing the concrete in front of the slip form, you want to make sure you have small overlapping piles. You don't want a whole lot of lateral movement of material. Lateral movement can cause segregation, which is not desirable. And also, if you're going to put dowel bars into your overlay, you should design that dowel bar placement as if you were doing a full depth pavement requirement. So when you're doing your analysis and you determine that optimal steel depth, it'd be the same as doing a traditional pavement. That's where you place the dowels. Once the concrete has been placed, they recommend either using longitudinal tining or burlap or turf dragging over the surface so you get some effective texturing. But this must be performed at the right time. If you do it too early, you're going to rip up your surface. If you do it too late, you're actually not going to get the benefits of that texturing. After it has been textured, you do want to make sure that it's cured properly. Because these overlays are a little thinner, you have a very large surface area compared to the volume. So just like you want to make sure you have a moist surface underneath, you want to make sure that it's not too dry on top, because you could have excessive curling and warping if that water starts evaporating from the top too quickly. So if it's very hot, you can fog spray an evaporation reducer, or you can put some sort of sealant on. And that's what you see there in the picture below. You have your slip form paver going away from you in the background, and in the foreground you have your a machine that's spraying that spraying a curing agent on top to make sure that water doesn't evaporate. And then the last thing during construction that's important is your joint sign. You want to make sure that you saw before your curl stresses exceed the bond strength. If you wait too long, if you have a bonded pavement, that'll simply pop off of what you're trying to bind it to beneath there, unless you saw it on there, and then you'll have that good bonded surface. If you do saw too late, you can have excessive stresses and also random cracking. Now, since I only have 3 minutes left, I apologize. There were some good questions and discussions during the presentation, but I think I tried to cover too much material. The table you see here is within the Technology Center's document, so I'm just going to skip over that. But they do have joint saw cut depths for conventional saws, for early entry saws, and then also longitudinal and transverse information. And they have different requirements for both bonded and unbonded overlays. So all that information is within the document that I put in the chat box, so I'll just skip over that now. But I did want to show this very nice picture of a nice joint that was cut and then the crack that developed. This is why you want that larger aggregate, because that crack that developed below the joint, that is going to have load transferred through the aggregate interlocked, which is critical for good pavement conditions, or pavement performance, especially if you don't have dowel bars. So in summary, I will email you your professional development hours after the presentation, no later than Friday, May 9th. You can rewatch the Pavinars through the old website, so the pavinars.uark.edu. That is where all the Pavinars will be archived that have been shown to date. The next Pavinar is Tuesday, August 5th, and the topic is Towards Zero Deaths, What Can Pavement Engineers Help With? And as I mentioned last time, this is the last Pavinar that I will be doing. Dr. Danny Xiao at Louisiana Transportation Research Center is taking over the series, which I really appreciate him doing. And he set up a new website, the www.pavinars.com, and I encourage you to continue joining these sessions, because I've heard nothing but good feedback on this, and I hope that the series continues on strongly. So that was a brief overview of Portland cement concrete overlays. I got 1 minute left. I'd be more than happy to take any sort of questions or comments. Thank you to Judith Shaw for the comment, but if you have any other questions, please feel free to stay on, and I'll answer them as they come. Thank you very much, and have a great summer. Well, there don't appear to be any questions. Oh, there is one from David, and I apologize. Can geotextiles or fabrics be used in lieu of hot mix asphalt for the asphalt layer? And the answer is yes. And the Technical Center actually had a section on geotextiles or fabrics. I just didn't feel like I had enough time to cover that in an hour. But yes, they have been used, and they have been used successfully, both geotextiles and fabrics, between the two concrete layers. All right, well, thank you everyone to join, and if you do have any lingering questions, I'll stick around, but as I mentioned, have a great summer.